In this example, we're going to go through what's called the wire and loop problem. This is a pretty important problem to understand. It's an application of Faraday's law, and it has a lot of different twists that it can take. So I'm going to read the setup, and then we'll talk about possible things that you can do with this. So it says that you have a very long wire that carries a positive current in the upwards direction, as shown in the figure. A conducting rectangular loop is next to the wire. On the diagram, we're going to sketch several vector symbols to show the direction of the magnetic field within the loop. The relative sizes of the symbols should indicate how the strength of this field changes. So first off, just know that the magnetic field is being produced by this wire, which is going and carrying the current upwards in the page. We know that for long straight wires, what they do is they produce circular magnetic fields, right, that follow the right-hand rule. And so the magnetic field of any long straight wire is just concentric circles. And so what will happen in this picture is that the magnetic field to the right of the wire is going to be going into the page. And because the field gets weaker as you get further away, you've got kind of a field which is changing in its strength. So I'm going to draw symbols inside of this rectangular loop of wire, which is just sitting here. And I'm going to show the fact that the magnetic field is getting weaker as you get further away. So these X's represent the magnetic field kind of from the wire, right? And you can draw some more up here too, right? And so the challenge with this problem is you definitely have a flux that's coming from this magnetic field. It's passing through a closed loop. And the questions would be, how can this flux change so that you could produce some type of an EMF in the loop and drive current through it? It is sometimes helpful to kind of think about the loop. I tend to like to think about the loop having some type of a resistor in it, which I'm just going to put up here as an R. Because usually, a loop is going to have some type of a resistance, and that resistor is going to feel the EMF that gets induced. All right, so let's take a look at how this is actually going to take place. So question 2, in order for a current to be induced in the square loop, or the rectangular loop, what must happen? And of course, according to Faraday's law, we have to have a change in magnetic flux. So what Faraday's law says is that you need a changing flux. All right. So if this wire is carrying a steady current, nothing's going to happen. Now, how can this happen? How can you have a changing flux? Well, there's a lot of things that can happen, right? One thing that you could do might be, let's see, 3 ways, right? One thing you could do is you could actually move the loop sideways. So if you move the loop to the right, you're going to decrease the flux. Something else you could do is you could change the area of the loop by stretching it or squeezing it. That's a possibility. Right? That would also change the flux. And there's even another way, and the other way would be if you somehow were to change the current in the wire. Because changing the current would also change the amount of magnetic field that goes through the wire. So there's a lot of things that can happen, and you'll see different problems where you can change one of these things and see what happens, what kind of EMF you generate. We're going to choose one of those today in this example. Like later you'll see we're going to choose the last one, but you could easily adapt this to other ways, other changes as well. All right, so those are the things that could happen. Let's take a look now for question 4. Question 4 says write an expression for the magnitude of the magnetic field a distance r from a long straight wire that carries a positive current in the upwards direction. This is a formula that you should have memorized. And so I'm just going to write that one down. This is one we learned about a month ago. So for a long straight wire, the magnetic field does this. And the r in this formula, the r would be kind of the distance in our picture. I'll draw it up here. That would be this distance away from the wire. And of course I is the magnitude of the current passing through the wire. So we know that the magnetic field gets weaker, right? As r gets bigger, the magnetic field gets stronger, and that explains our picture that we drew up here. So now let's go and let's imagine we have to come up with a way to find the actual flux through the loop. So question 5, consider a calculus thin vertical strip contained within the loop as shown in the figure. This strip is parallel to the wire, and it has an area equal to L dr. So L in my picture is going to be kind of like the height of this loop, or we'll call it the length, parallel to the wire. And dr is going to be this little thickness inside of here, which we're going to say is something we can make calculus small. So the area that we're talking about, the L dr, is going to be the area of this shaded area. L dr, that's kind of like the dA here, right? Because it's a very thin rectangle. So the question then is this: what can you say about the magnetic flux through such strips moving from left to right across the loop? And I hope you can agree that as you move from left to right across the loop, the magnetic field's getting weaker, as we discussed. So you're going to have less flux as you go, right? As you move to the right, from left to right. All right, because you've got the same area in each strip, but you have less magnetic field passing through it. All right, so now you probably want to take a quick look at this picture and get familiar with some of the details. We have other things going on here as well, so let's look at our variables. We've got r, of course, which is the distance from the wire. I hope you can imagine that r is going to be something that we're going to integrate over. And we're going to let r, probably in an integral, start from a distance a and then end at a distance b away from the wire. So a and b kind of define like the left and the right edges of the loop. And keep in mind that L is kind of the vertical dimension of the loop. So those are all pretty important variables here. All right, so to determine the magnetic flux through the strip that's shown in the figure, let's see, you can simply multiply the expression from 4, which was the magnetic field strength, times the area of the strip. And we're going to do this, and we're going to call the resulting flux just kind of a D flux. Okay, so we're going to have basically the magnetic field here, and then we're going to have an area here. So I hope you recognize that, you know, this first term is kind of like our B term, our field strength. This second term is going to be kind of like our A term. And of course you multiply those two things to get flux. And the way that we've written it is we've actually kind of made dr something that we're going to integrate. And so this flux that we're getting when we multiply these two things is simply the flux just through one strip, right? So this is kind of a D flux right there. It's just that one strip. And of course we have to add up all the strips going from left to right. All right, so we're going to move on and do that. And so question 7 says, determine an expression for the total flux that passes through the loop. And this means we have to integrate our expression. So of course we're going to do total flux here. That's got to be the integral of all of the strip fluxes. Okay, and so I'm immediately just going to go ahead and substitute in the expression from the last question. So here's the current part. And then here is the area part. Notice that the language of this integral is dr. So we want r to go from A to B. Those are specific distances from the wire. Okay, so if you like, this is kind of like lowercase r is equal to A. That's your lower limit. And this one up here would be lowercase r is equal to B. So the variable of integration is radius here. All right, now at this point, we're going to factor out some things. Of course, you can factor out the constants. And let's see, we're going to factor out anything else that's constant, that's independent of radius. So, of course, the current in the wire is independent of radius. The length of the wire is independent of the radius. But you've got to keep that inverse R in there. And so the integral that we have to evaluate is just the integral of the inverse of R. And that's a pretty easy one. I hope you know that one already. That's the natural log. So ln, and because you're subtracting, you're doing a quotient. And so this is an expression that would allow us to determine the total flux, right, through a rectangular loop where the length of the loop is L, and then the left and right edges are given by A and B, and you've got a current there. So that's a pretty handy expression. So that's kind of the tough part of this problem, is coming up with that. So this is a big deal, right? That's your total flux. All right, now to finish this, I said if you go back to earlier, we said that there were many ways that you can change the flux through the loop. You can move the loop, you can stretch it or squeeze it. We're going to look at what happens if you change the current in the wire. We'll just choose that for this example today. And so number 8, if the current in the wire changes with time, in other words, if it's a function of t, use Faraday's law to determine expression for the induced EMF in the loop. And so what we'll do is simply take our Faraday's law and we're going to apply it. Take that negative derivative out, and we're just going to stick the that expression in for the total flux. This is a 4, whoops, that's a 2 pi L N B over A, and you might be thinking to yourself right now, hey, he just forgot to write down the I term that was in there. In fact, I didn't. I'm going to just pull that out. Let me actually just put that at the end here, inside, because this derivative, when you look at it, is only going to be acting on the I, because that's the only thing that changes with time in the example that we have selected. So this whole expression, actually what happens is that, the negative comes out, and everything else that we had in brackets kind of just pops out. And the derivative dives in and really just focuses in on that that I term, okay? And that's how you can deal with this. So I'm not going to work out all the details, but let's just say, for example, that the current might be decreasing exponentially, so that you could say I is equal to, I don't know, let's just say 5 times e to the negative t, right? So just as an example, right? That's a time-dependent expression for the current. So if I were to say what's the EMF that's generated by this situation, what you would have for the EMF would be all of this stuff, right? That would drop down, and then you would multiply by the derivative of this current, which of course is just going to be equal to negative 5e to the negative t. So it's all this stuff in front multiplied by that, and that's how you apply it, okay? And exponentials are nice because the only thing that comes down is the little exponent thing up here that multiplies the t. So you can imagine lots of different expressions you could come up with that have I as a function of t, but that's how you would deal with coming up with your EMF. All right, the last few questions here are just kind of directional questions to get us to remember about the directions of things. Number 9 says, assume that the area vector from the loop points towards you. It's out of the page. And I'm not going to you can look at the picture if you want, but let's say that our area vector was coming out like that. And then you say, well, the magnetic flux, what kind of flux do we have in this case? Is it positive or negative? Well, remember that all the B fields that we're going through were like this. And so the flux in this case is definitely going to be a negative flux because you have opposite directions between the area vector and the B field. So that's like a cosine of 180. So that's a negative flux. Now the next question is related. If the current is steadily increasing, so let's say that it's increasing, unlike our example up above, but let's say the current is getting stronger and stronger. Well, what's going to happen is that the flux itself is going to be getting more and more negative. So if the current is increasing, this B is going to be growing, right? It's going to be getting bigger and bigger into the page. And so the rate of change of the flux is going to be negative because you're going to have more and more negative flux every second. And then going back to Faraday's law, remember Faraday's law, basically it puts an extra negative in front here because Faraday's law is talking about nature opposing a change. So according to Faraday's law, the EMF is going to be positive. And that's because essentially like you have an EMF is equal to a negative of another negative. And if you think about that, why is that useful? Because that tells you that the current that's induced is going to be counterclockwise. Remember, we chose the area vector to go this way. This is our area vector. And if your thumb is pointing out, then counterclockwise is positive. And so since the EMF is positive, that means that the current will flow in this direction of positive, the positive direction. Okay? And so that is kind of the idea. So in our loop, in this example, if this is the rectangular loop, what's happening, of course, is the current that's induced is going this way. That's what's going to happen. And the point of that current is that the current is trying to produce a magnetic field that resists what's actually happening. It's trying to maintain the status quo. Remember that the external field is getting stronger into the page, and if you check with your right-hand rule, this magnetic field that's induced is actually trying to work against that. And so the induced field comes out of the page. And that's consistent with what we've learned about Faraday's law. And 13, to wrap it up here, what if you initially selected your area vector to go into the page? You could have done that. And if you did that, I'll kind of leave it to you to show that there would be no difference in our final answers here. So this would not change. It would not change the final result that we came up with. In other words, it would not change that. And I'll kind of leave that to you as an example to work out just with the right-hand rule. So simply choosing an area vector to go one way or the other will not affect the physics of what's happening. You'll get the same answer at the end. All right, so I hope this was helpful, and we'll see you in class.